Hello and welcome. In this video, we are going to take another look at our current P5 that focuses on the calculation of some geometric properties associated with various cross sections. Particularly in this video, I'm going to focus in on the calculations associated with a circle 2D. This is going to be the version 4 of this function. This version of the function uses parallel arrays. We're going to see how we're going to leverage that. And this video assumes that you've been following along with the earlier videos and have already set up your P5 and have possibly completed your P3 modified so that you see how we're actually going to use for loops. Now, in this video, I'm going to actually do our circle 2D V4. I'm not going to do much of the testing or anything like that in this video. I'm going to leave that for another video when we jump back out to the main. What we're going to do is we're going to focus solely on our calculations and how we're going to validate the input arguments. And so before we leave this spot right here, we want to take a quick look at our input arguments. We have a radius max, our radius min. We pass then several arrays, parallel arrays. Why do we call them parallel arrays? Because the idea is we want to synchronize the indexes between all of them. So in other words, the 0th element of the radii corresponds to the 0th element of the edge, 0th element of the array, 0th element of each of our i's or our second moments of inertia. And in the end, will simply tell us how many of the elements in the array we're actually going to use, which essentially conflicts or contradicts, I guess you could say, with the n max. The n max is the amount that we have allocated to the array. And as long as our n is less than or equal to our n max, then we should be able to update each one of these arrays. If we try to use an n that is larger than the n max, then essentially we're going to be stepping off the edge of our allocated memory, and essentially what we could end up doing is violating other variables' memory. In other words, we could be reaching in and changing their values without meaning to do so. So it's going to be very important that we check a couple of things here. First thing that we're going to want to check is to make sure that the radius max and the radius min are both in fact greater than 0, and also that the radius max is greater than the radius min. If any of those conditions are false, then we need to prompt the user and say something's wrong. Also, we want to make sure that the n is arbitrarily. We could technically do only one calculation, but what we want to do is we want to assume that the user intended for this to be multiple values, and so we need a minimum of n equal to 2, and we also need to make sure that our n is in fact not greater than our n max. Now, let's go ahead and jump on down here to the function. We've said a lot here. Let's go through and do it. So the first thing that we want to do is we want to start by checking some of the input arguments. Now, it doesn't really matter necessarily in what order you do this. Just make sure to capture as many of the possibilities as you can think of, which I've described earlier. And so what we'll do is we'll get started looking at the radius max and the radius min. Now, you've got a couple of different ways you can go about doing this. You can write what I call positive logic. In other words, we look for affirmation that the values are correct, or we can do what I also refer to as negative logic. In other words, we look to exclude values that are incorrect. And that actually makes our code a little bit easier to write. What I mean by that is basically we want to check to see if our radius min is less than or equal to 0. In other words, we don't want values that are negative, and we arguably don't even want a value that is 0, although technically that would work and kind of still makes sense. But again, we're making some rather arbitrary assumptions here, likewise for our n, and we'll see in just a second. And so what we'll do is we'll use this negative logic, and what we'll do is we'll actually check 3 conditions, starting with our radius max. And so if our radius max is less than or equal to 0, or the next condition we want to check is that our radius min is less than or equal to 0. And then the third condition that we want to check using our OR is actually to check to see or verify that the radius max is in fact greater than the radius min. So the easiest way to do that, again, using this negative logic approach, is to see if our radius min is greater than or equal to our radius max. Now, I encourage you to pause the video at this point and just check to make sure that this makes sense to you. These two probably make the most sense. In other words, we're looking to see if the user provided 0 or a negative value. And then in this particular case, then what we're doing is we're checking to see, did the user provide a value for radius min that was greater than or equal to the radius max? And again, if any of those conditions are true, we simply provide a printf to the user that says error or reminder or warning, but definitely don't proceed. And that is that our radius max must be greater than our radius min and radius max greater than 0 and radius min greater than 0. Now, if you don't like having all of this in one printf or in one if statement, that's perfectly fine too. You can check these conditions individually. I would actually make a pretty strong argument that that is a good idea because it refines the feedback back to the user. In other words, you're more informative to the user as far as what they've done wrong. So again, we're just keeping this one simple here for brevity in our video. But then what we want to do is we want to look at the next thing that we want to check. And again, a compound condition. We are going to look at our n. And so the first thing we want to check to see is the n less than 2? And again, we said that that was going to be kind of arbitrary, meaning that we did want for this application to have at least 2 values. In other words, one for radius min, one for radius max. We could technically come along and change this a little bit. In other words, we could have the condition in which the radius min was equal to the radius max, in which case we're only making one calculation. But again, for the way that we have described this, we need to have at least 2n. But on the other side of it, we can only have up to n max because that is what we've allocated for our array. Again, we're using static arrays, not dynamically allocated memory. And so for right now, we need to make sure that the user doesn't ask for more than we can give them. And so the easiest way then to check that is simply if our n is greater than our n max. Again, I encourage you to pause the video here and make sure this makes sense to you. Effectively, we just want to make sure that the user does not enter in a value for n that is inappropriate for our calculations. And again, what we'll do here is we'll simply provide a nice message back to the user. Error. How about we say something like n must be greater than 1 and less than or equal to, and in this case, I am going to put a little bit of extra in this one, and that is I'm going to go ahead and put a %d in here, and that %d will allow for us then to not hard code the value for the n max. In other words, if we decide later on that we want to change our n max, well, that's perfectly okay, and we don't have to go back through and then change all of our error messages. Now, the one thing that we did not do in either of these negative statements, if you would, in other words, if either of these ifs were triggered, we need to go through now and we need to change our results equal to exit failure. In other words, now the calling function will know that something went wrong inside of this little helper function that was doing the calculations. In other words, it was not able to complete its job. Under the else branch now is when we will actually go about doing the calculations. Now, unlike our P3 modified, which if you have already completed it, we can take a quick look at it. you can navigate to function, and you'll see that we had to go through and declare some extra variables. Now we'll still need some of these, okay, but we will instead use the variables, excuse me, that were passed in the function signature. Now we'll probably still want a radius delta because that will make it rather convenient for us, as well as an index. But you're going to see that instead of these individual ix, iy, and iz, what we can do is we can actually update our vectors as we are going along. So let's get started on this. The first thing that we want to do is go ahead and have our index variable that will simply allow for us to loop through our for loop up to, but not including, the value of n. We'll come back to that in just a second. We probably also want to have a double for our radius delta, which is basically going to be then, based on the n, it's going to be then the difference between adjacent radii in our calculation. And a convenience variable that we technically do not need will be our radius current. And again, you'll see why that's a convenience variable, but that is one that we probably do want to have. At this point, we probably don't need too much more out of our P3 modified. Perhaps just a simple reminder of some of our formulas. You'll notice here that our edge is now 2 times pi radius current, or 2 pi r. The area, pi r squared. The one that you're probably not as familiar with is going to be our ix, iy, and iz. The ix and iy is going to be pi over 4 radius to the 4th, as well as our iy, pi over 4 radius to the 4th, and then iz, pi over 2 radius to the 4th. All right, so let's go ahead and do these. We'll jump down here. We'll start by setting up our for loop, which initializes at 0. It continues up to, but not including, n, and we simply increment it 1 by 1. And now inside of this for loop, we can first do our calculation for our radius current. Our radius current is going to be equal to our radius min plus some multiple of our radius delta. Now, we have to go back. We skipped a step here on accident. We will go ahead and calculate now our radius delta. Our radius delta is simply going to be the difference between our radius max, which is guaranteed to be larger than our radius min. And the only tricky part here is going to be to understand the relationship between the number of data points and the number of segments. Number of data points is n, and the number of segments is going to be n minus 1. And so now we've got a value for our radius delta that can be used in our calculation of the current radius. And again, this is kind of a convenience variable. You'll see why in just a second. But what I want to do is I now want to populate or update each of the elements in our parallel arrays, starting with the radii. And so the idea here is I want to keep track of each individual radius. And I can do that by using the vector radii, square brackets index is simply equal to our radius current. Now, hopefully at this point you can see why I'm saying this is just a convenience variable. It just shortens our code ever so slightly. We can actually use the value once it's stored in the array in the future calculations. But again, for convenience and also for cohesion with our prior example in our P3 modified, we are going to use this convenience variable, this radius current. So let's go through now and do the others. We'll start off with our edge. And again, we said our edge is going to be equal to 2 times I times the radius. So it's just simply going to be 2 times then our constant m pi times our radius current. And again, what we're going to do is we're going to assign it to the corresponding location in our edge parallel vector. And so now you can hopefully start to see why I refer to these as parallel vectors, because they effectively use the same index across multiple vectors and sort of keep this in lockstep or synchronization between all of our vectors. And again, here we'll do our area square brackets index. And then in this case, it's going to be pi r squared. And so in this case, again, we're going to have our constant, and we'll use the POW function. And again, our convenience variable radius current raised to the second power. At this point now, we can jump into some of the less familiar variables, our IX, or rather less familiar formulas. Then we're going to be interested in our M pi. And how you choose to do this is up to you. I like to use an abundance of parentheses, although not completely necessary here. We will do the numerator here. So it's going to be M pi times the POW of the radius current. In this case, raised to the fourth power, all divided by 4. This formula is actually the same for our IY. And our IZ is slightly different. With the denominator simply changing to 2. Now, if we don't have any typos, believe it or not, we are done with our function. Again, what we've done is we've updated 1, 2, 3, 4, 5, 6 parallel arrays using the n to say how many calculations we want to do across our radius max and radius min, or put another way, starting at our radius min up to our radius max. Now, at this point, if you were to go back to your P3 modified, you're probably convinced why parallel arrays are very useful. And we haven't even gotten yet to the point of printing either to the console or to a file. But you can just take a quick look to see how much less code you have as opposed to your P3 modified. Now, again, we haven't gotten to the printing portion of it yet. That will change a little bit. It will still be a fair amount of code, but hopefully you've got now a good understanding of how parallel arrays work and complete the other functions with the other calculations. So as always, hopefully you found this video useful. If you have any questions, comments, or concerns, don't hesitate to email me, and thank you for watching.